Yeah, we are now trying to prove concentration phenomena for Gaussian random vectors. And at the moment we are trying to do this for linear functions of them. So maybe let me recall what we are going to prove, and where we also want to develop some tools which work more general, but in particular we want to prove this situation. So we look on a Gaussian random vector which has a normal distribution in p dimensions. So that's the simplest one. So namely, the means are all 0 and the covariance is the identity matrix. So this just means all the components of my vector, of my p-dimensional vector, are independent, and each of them has a standard Gaussian distribution. Okay, and then we want to show that the norm of such a guy concentrates at the or around the expectation value. And the expectation value of this is p. So what we want to show is that the probability of the vectors in R to the p, and probability measured with this distribution, so the probability of those vectors for which the norm has a small distance to the expectation value. Okay, the square of the norm has the expectation value p, so the norm itself should be close to the square root of p. Square root of p is not exactly the expectation, but the guy should be close to this, and deviation from this, so that this is bigger than epsilon, this we want to estimate by 2 times e to the minus epsilon squared. And last time I think I wrote here 16, now I think I prefer to have here 8. At least that's what I hope to prove later. Okay, but I mean, all those small constants are not so important. Very often in books you find there is a constant without being specific. Okay, but here I think it should be 8. Okay, so that's what we want to prove, and actually we want this for epsilon between 0 and small. Here means actually it should be small compared to this one. So I mean epsilon here is not close to 0, because otherwise this would not be very interesting, but it's far away from this guy. So it could be 5 or 100 or something like this, and when p is very large, 100 is still small. So I rewrote this also in a rescaled version, dividing by square root of p, and then you see much better that you can have a small epsilon here. Good, okay, but yeah, maybe let me do it also in a rescaled version, because maybe this is more somehow intuitive. So I wrote it with the x twiddle. So the x twiddle, that's the rescale. So this is 1 over square root of p times x. So this is where all the components have variance 1 over p. And for those, this estimate goes over to that x twiddle. Yeah, the norm of x twiddle is close to 1, and then the deviation from this, if I call this now epsilon, then this can be estimated by 2 times the exponential minus p times epsilon squared, and here it should also be over 8, not over 16. And now epsilon can here be a really very small quantity, because you see, if epsilon is small, eventually the p will be overwhelmingly large, and you see how this goes exponentially in the dimension to 0. Good. Okay, so I already started to prove this, and the first step, trivial step, was instead of doing something for the norm of x, we wanted to do this in terms of x squared, because x squared is really the sum of independent things, and that's what we can control. So we started with, yeah, I mean, by estimating, but this was very simple, that if I want to compare the norm of x with the square root of p, I can estimate this by the corresponding problem, where I estimate the norm of x squared minus p against, of course here I need bigger than epsilon, and here I compare it. Here the epsilon is replaced by epsilon times the square root of p. Okay, so I mean we want to show that this is smaller than this, but what we are going to do is to show that this actually is smaller than this, and then we also get the other thing. Okay, good. Yeah, and the point was now that x squared is the sum of the square of the components, and the components are independent. So what I have here, x squared, is really a function which is given by a sum of independent variables. And that's something which we want to use for this concentration. Okay, but I started with very general estimates. So I had Markov inequality and Chebyshev inequality. And Markov inequality is maybe the basic one on which all the others essentially rely. So this tells me what does the expectation of a variable tell me about large values. And the expectation, because it averages and signs play a role, Markov inequality is only something useful, or says only something if you have a positive distribution. Because if you have a variable which takes on only positive values and you know expectation, then you know you cannot have very large values occurring with high probability, because they would move the expectation in the other direction. Okay, but this was made precise. Then we had Chebyshev's inequality, relying on this, which tells us what the variance gives us. And now the general idea is that we should not just look on the expectation and the variance, but we should look on higher moments. Okay, and that's what we want to do. And this is the main tool we are doing to develop. So this will be then the main inequality. Okay, so the idea is we should look on higher moments, but dealing directly with moments is quite tough. Even for the second moment, it was the variance, which is nice, because the variance of a sum of independent things is the sum of the variances. For the second moment, if the first moment is not zero, this is not true. And if you have higher moments, I mean the kth moment of a sum of independent guys is not the sum of the kth moment, but it contains all the lower ones. So this is getting complicated. And for this, it's much better to go to the moment generating function. Okay, which in principle is like the Fourier transform. We are packing all the moments into one function, and because this is an exponential function, this really goes nicely with the independence. Okay, so I mean, what we are going to do now, we are looking on all moments simultaneously. Okay, but we are packing the information about the moments essentially into the moment generating function, or more or less the same as the Fourier transform. Okay, so I mean the setting, so this is still a general setting where I call the vectors y. Let's say y is my random vector in R to the p. And I have a function of this vector, which of course later on will be a linear function. Okay, but still we can do it more general. So it's a function from our p dimensions to R, and then I'm looking on the moment generating function, and with this I mean I take the expectation now of the exponential function of lambda f of y. So f of y is the quantity in which I'm interested. Okay, and now I take just for any lambda here, I'm putting here lambda. Lambda is parameter which I choose later in such a way that I get the best possible information. So I consider the exponential lambda times my variable, and I take the expectation of this. And this, if this lambda if you would replace this by I times lambda, then you would have the Fourier transform. Okay, but here we do it with without the I. But essentially this is the Fourier transform. Okay, and of course we are using essentially the main property of the Fourier transform, or the characteristic function, how it is called in probability, how this goes with the sum. Okay, but we just see this directly. And maybe just let me expand the exponential so that we see that this is really a generating function in the moments. Because I mean, what I have here is the exponential, the expectation, and the exponential of this. Of course, if I do the power series expansion of this, is the sum from 0 to infinity of the argument to the power k, and the argument here is lambda f of y to the k divided by k factorial. That's just the expansion of the exponential function. Okay, and then I mean everything here is nice, so I can here commute the expectation with the sum. So what I have here is really the sum, and then I get, I mean the expectation only applies to the y. So lambda is just a number, so I get here lambda to the k, and then the expectation acts on f of y to the k, and then I divide by k squared. And of course this here is just the kth moment of this variable in which I'm interested. So this here is the kth moment of the variable in which I'm interested in f of y. Okay, and so you see I have here all the moments, but by choosing lambda I can somehow put different, I can choose the way which I put on the moments. So I mean, which contributes the most to my contributions. I have the freedom of shifting the emphasis a little bit. So all moments play a role, but by choosing different way lambdas, I'm shifting which play more role. And okay, and so that's why I put a lambda here. So I will choose this later in such a way that I get the best possible information out of this. Okay, so this is called a moment generating function. I mean, you could also do it without this, then it would also be a moment generating function, but we take the exponential function because this goes very nicely with the sum. Okay, so and now we want to apply essentially a Markov to this function. I mean, Markov, essentially we have it for any random variable, and what we did also for getting Chebyshev was we applied a monotone function to our guy, because this doesn't change the inequality. And so this function here, where lambda goes to this guy, this is monotone if lambda is positive. So in the following, I will consider lambda positive. And of course in Markov, of course I need a positive function. Okay, but the exponential to anything is also positive. So I'm in the context. So this function is a good function for which I can apply the Markov inequality, because this is a positive function. But of course I'm not really interested in this function, but I'm interested in this. But going from f of y to this is a monotone mapping if lambda is positive, because the exponential function is monotone increasing for positive lambda. Okay, so I mean, so for each lambda in R, I have that this function here, the exponential lambda f of y, independent of the value of y, is positive, which means I can apply Markov to this guy. And I also use that if lambda is bigger than 0, then this function, if I'm going over from something to exponential in lambda times this something, that this is a monotone increasing function. Okay, and this of course I need in the following by comparing f of y with this exponential function. Yeah, so namely, what do I want? I mean, what I want is estimate of the form. I want to estimate the probability that f of y, let's say, is bigger than alpha. That's what I want to see whether I can deal with this. Okay, and now I go over to this exponential guy, and I mean, if this is bigger than this, then e to lambda times this is bigger than e to lambda times this. That's the monotonicity which I'm using here, that I'm not destroying the direction of this. So this here is the same as the probability that I'm looking, instead of fy, I'm looking on e to the lambda fy, but then of course I have to ask that this should be bigger than e to the lambda alpha. Yeah. Okay, so because for each y this inequality is the same as this inequality here. Okay, but now I have here a positive function with some distribution, but now I can apply to this Markov property. And for Markov property, I estimate probabilities that my variable is bigger than something against the expectation of my function divided by this something. So Markov tells me exactly that this here is less than the expectation of this guy, the expectation of e to the lambda fy, and then I have to divide by what I have on this side. I divide it by e to the lambda alpha. Good. Okay. And so this inequality is true for any positive lambda. Okay, so I'm free to choose the lambda, and so of course I'm choosing the lambda where this side is the smallest one. Or I can take the infimum over this side. I mean, this side doesn't depend on lambda. Lambda was arbitrary parameter which I have put in here to give me some freedom. So this means I'm optimizing this here over the lambda, and so what I get then finally is that the probability that f of y is bigger than alpha can be estimated, and I'm taking just the infimum of this side here over all lambda. So, and the lambdas which I can allow are all positive lambdas, and then I have here e to the minus lambda alpha, and I have the expectation of e lambda f lambda. Good. Okay. So this is nice, and this is more or less like Chebyshev inequality, that we can estimate this probability by something which contains the moments or whatever. Okay. But without further information, I mean without knowing much more about f of y, okay, it's hard to say something about this. Okay. So now we have to be more specific so that we really can make concrete use of this. So this is a very general estimate, very powerful, but of course you must be concrete what is the nature of your variables. And in our case, this f of y is now really the sum. I mean, this is true. I mean, here I just have a variable which I write as a function of something, but it's just the distribution of this variable plays a role. But now I want to use that this f is really the sum of independent guys. Okay, so now we really invoke more specific information, which we have in the situation where f is the sum of the squares of my coordinates. So namely the y, the underlying y, is actually has independent coordinates. So y, and the coordinates of this I call S1 up to SP, has independent coordinates. So this means the distribution of this factorizes into the corresponding product of the distribution of each of the components. So the density for this vector Sy up to Sp is actually a product of a density for the first component times a density for the second component times, and so on, a density for the last component. Yeah, okay. And of course in our situation all these densities are the same and each of them has a Gaussian distribution, but maybe let us still do it in this generality where I'm not really specifying exactly what this is. Okay, and so this is about the y, the underlying distribution. So this consists of independent components, and then the f is the sum of something on these components. So what we have about the f, the function, so this is a sum of functions of the coordinates. So this f, this is a function of all my coordinates, but now we are in a very special setting where actually it's a sum of the coordinates, but okay, it can be functions of each of the coordinates. So it's f1 of s1 plus and so on, fp of sp. Okay, and in our specific situation again, I mean the f's are here are all the same, and each of them is just the square essentially of the s, because I mean the norm squared is the sum of the squared of the coordinates. So those f's here are essentially the square of the coordinates. Okay, but still we can now really say, continue essentially the discussion above. yeah, in this generality, because now we can say more. Because now, of course, if this f of y is a sum, then this exponential function now splits into a product. And we can essentially go back to information about each of the coordinates. Okay, so our situation is we have this in general, but now I have more specific information about my distribution of the components and also about this f, and then we take the expectation of e to the lambda fy, but this is then of course a sum, so e to the lambda fy. So what is this? So this is e lambda, and the f is now a sum, so it's a sum of f1 of the first component plus and so on, plus fp of the last component. Yeah, and of course now it's really, that's the reason why we have chosen here the exponential function, because now e of a sum is the product of e to the factors. So this here is now really just e to the lambda times f1 of s1 times and so on times e to the lambda fp of sp. Yeah, and now if I take the expectation, then of course we can now use the independence. So here I have used the linearity of my function, but now I'm using the independence of the coordinates. I mean the coordinates are independent, and this means a function of the coordinate, they are also independent. So this means the expectation of this product of independent guys just factorizes into the expectation, into the product of the expectations. So this means the expectation of this guy here, e lambda fy, is now really just the product of the expectation of e lambda f1 of s1 times and so on the expectation of e lambda fp of sp. Yeah, and now you see we are now essentially back to information about the distribution of each of the variables. Okay, and so now of course, if we now want to go further, we have to control this. In our case, of course, the f's are all the same, so essentially this here, each factor will be the same, just depending on the distribution of each of the variable. And now the question is, can we calculate this, or at least estimate in such a way that this here gives us a useful a useful estimate. And I mean, of course, we want an exponential estimate, which should, of course, e to the minus something. Okay, so here we have something like e to the minus, that's okay. But here, of course, this will explode. It will more go like e to the, and very often it goes like e to the lambda squared. But that's actually something, the combination of this, which we can control. Okay, and that's actually what happens in our situation. So I mean, so the idea is that those terms here, I mean, they will grow, but they should not grow so fast that this exponential decay here totally disappears. So they should grow in a way that the whole thing is still controllable, and we get exponential estimate. So those terms here, if we want to use this somehow, I mean, of course, this here is true in general, but we need now specific information about this to use it, and this specific information should be of the form that those guys here, they should not grow too fast in lambda. And often, and actually what they do, they should go like e to the lambda squared times a constant. Okay, that's something which we expect, and why do we expect this? Because that's really something which happens if I take the moment generating function of a Gauss distribution. The Fourier transform of a Gauss has really this behavior. So maybe let us check this. I mean, here later on we will not take e to the lambda times a Gauss, but we have the square of a Gauss. So and later we have to calculate this, but maybe just to see that maybe the thing we should expect from such a thing, let us calculate it in the simple situation where S has a Gaussian distribution and F is just the identity. Then essentially we have the Fourier transform of the of the Gauss distribution, and this goes like e to the lambda squared. Maybe let us just check this. So maybe you have calculated the Fourier transform of the Gauss at some point, but if not, so let us essentially do it. So note that for Gauss distribution, we can really calculate this guy. So I mean, so there we have to take the expectation now over a Gauss distribution in one dimension. I mean, those guys here are one-dimensional. So I take 1 over square root of 2 pi, integrating. Then I'm integrating e to the lambda. And now f1 of s1, that's I assume this has a Gauss distribution. So this has a t, and the density of this is e to the minus t squared over 2. So that's what this expectation means if f1 of s1 has a standard Gauss distribution. And of course, this is something which we can calculate. So namely, what is this? This is 1 over the square root of 2 pi. Okay, and I mean, we can integrate this thing over all of r. Here we have a linear term, but of course we can shift by using the binomial formula. We can write this again as the square of a shifted variable. So namely, I'm writing this here as e to the minus t minus lambda squared divided by 2. So I have the e to the minus t squared over 2. The square applies here to everything. And this term here, this is the gross term here. I get 2 times t times lambda divided by 2. The 2 goes away, and the minus also goes away. So I have this term. But of course, I'm missing the term is the lambda squared, so I correct by this here. So I also have here the e to the lambda squared over 2 dt. Okay, but this correction by lambda squared is not a problem, but this doesn't contain a t. And now you see where I get the lambda squared. So this is the same as this, but now I can take this out, e to the lambda squared over 2, and I'm left with, essentially the integral of e to the minus t squared over the real axis just shifted by lambda. But if I'm shifting over r, I mean, if I'm integrating over r, a shift doesn't make a difference. So I have here e to the minus t minus lambda squared divided by 2, integrating by dt. And if I replace t by s, which is t minus lambda, then it's just this integral here. So this here is just 1. This here is just 1. Just the integral over the whole mass of the Gauss distribution. And I'm left with e to the lambda squared. So you see, in the case where I have here a standard Gauss distribution for f of s1, I really get a growth like e to the lambda squared. Okay, and that's essentially the best thing I can expect. Of course, it would be nice if this would decay exponentially, but this is not going to happen. I mean, this thing here really increases in lambda, and it increases exponentially. And I mean, it exponentially in lambda squared looks worse than this decay here. But because we can choose the lambda, we can balance it in such a way that still we get exponential decay in the overall situation. Good. Okay, but now, I mean, okay, so this is just what we expect. But now we really should go back to the norm, the square of the norm, where we are writing it as the sum of the squares, and then check that also we have something like this. And then I still have to show that this is good enough. Good. Okay. But so let us do now really the calculation in this situation where we are interested. Okay, so let me specify. So in this situation, I mean, our random vector is now a Gaussian random vector. So all the psi's here are the same. All the components have the same distribution, and actually the density is the Gaussian density. And all the f's there are also the same, but they are essentially the square. So now we really treat this situation where my y is now really what I usually call x, the specific x, which has the standard Gaussian distribution in p dimensions. and where my f of x, so this is the norm squared. Yeah, and actually I want to estimate the norm squared compared to p, but here you see that the expectation, here is no expectation or something like this showing up, so I mean I should put this difference actually also here in this f. So really what I want to estimate is this quantity, and I want to see that this cannot become too big. Actually I want the absolute value of this. So for this I need two estimates, so it should not be too big in one direction and it should not be too big in the other direction, but this is symmetric. So essentially I have to estimate the probability that this is bigger than something, and I have to see that this can be estimated in an exponential way. Okay, and so this is the square, the sum of the squares, so this is t1 squared plus up to tp squared minus p, and now I want to write it as a sum of functions applied to each of the variable, and of course I have here the sum of the variables, but I also have this p, and if I want to have the same functions there, of course I can distribute the p by giving a 1 to each of the p components. So I'm writing this as t1 squared minus 1 plus t2 squared minus 1 plus and so on tp squared minus 1. Okay, and so this here will now be my function g of t1, the function g of t2, and it's the same function always, everywhere. So g of tp. So what I have here, the f's which I have here in general are all the same, and they are actually the function t squared minus 1. So the f1s up to fp are now one function which I'm going to call g, and this is just this here, so g of t is just t squared minus 1. Okay, and then the t's are the components, and of course they factorize, but they factorize into standard Gaussians, so the psi's I also know now very explicitly. So all the psi's are also the same, so all of the coordinates have the same distribution, so psi1 up to psi p is the same, and let me call it phi, and phi is just the density of the standard Gauss. So phi of t is just 1 over the square root of 2 pi e to the minus t squared over 2. Okay, so that's really the situation for which we want to prove this concentration. Okay, and now we have to see whether for this very specific situation we can also get our hand on this and see that it really behaves like e to the lambda squared. I mean that's the idea. I mean we cannot expect much better, but let's hope that it's also not much worse, so that we have e to the lambda squared, and then we really can continue. Good. Okay, so let us calculate this. And I mean, everything is here concrete, and integrals with respect to this Gaussian density we can do, at least if we integrate over all of R, so we really can calculate this explicitly here. So what we need is the expectation of e to the lambda g of t. T has a Gauss distribution, and g is just this t squared minus 1. So this is just explicitly integrating with respect to the Gauss density of over R from minus infinity to plus infinity. And here what is my function? It's e lambda, and this t of t is t squared minus 1, and the density is e to the minus t squared divided by 2. So that's what we have to integrate here. And again, you see essentially we are integrating over e to the minus t squared. Here's a little shift there, but this here is, what is it? Okay, we have here t squared, here we have something else, but this is just a factor e to the lambda, so it's the minus 1, it's e to the minus lambda, which can get out of the integral. So I have 1 over 2 pi e to the minus lambda. This comes out, and then the rest just is a multiple of t squared. Integral over e to the minus t squared over 2. Here I have it once, and here I have t squared. I have it with a plus sign here, so the minus sign here gives me a minus, and here dividing by 2, so I should multiply here with 2. Okay. Yeah, and now you see essentially I'm integrating again this Gaussian integral, but I have a factor here, but of course I can change my integration variable such that this guy here together is s squared, let's say. So let me say I call now t times the square root of 1 minus 2 lambda. I call this s, and then I have here e to the minus s squared over 2. And then just the dt is ds divided by this. So I will get the usual integral, but divided by this here. So, yeah, maybe, yeah, okay, maybe. Let me write this here. So this is the same as the integral now. So t squared times this here is now s squared divided by 2. And then I have a ds, but I also have, yeah, the dt is ds divided by this. I also have 1 over 1 minus square root of 2 lambda. Yeah, and I mean this integral, that's our usual Gaussian integral, which is exactly square root of 2 pi. I mean, that's a normalization of our Gauss distribution. Okay, so you see this goes away with this. And so what we are left with is just e to the minus lambda from here. And here we have this factor. So divided by 1 minus the square root of 2 lambda. Okay. And of course, this only makes sense if lambda is not bigger than 1/2. Because otherwise, this here would be negative. But then we also see that here I have something negative, and then I would have here an exponential guy. And if I'm integrating, increasing e to the t squared, then of course this is infinity. Okay, so I mean the sign of this has to be positive, so that I have here really an e to the minus t squared, which is integrable. If this here gets a negative sign, then I have e to the plus t squared, and of course the integral over this is infinity. So this means this moment generating function here, it only exists for lambda smaller than 1/2. Okay, but that's okay. I mean, here in our estimate, of course, we take the infimum, and so I mean, for the big lambdas, I mean, if you have here infinity, of course, that's not the lambdas which you should consider. We take here the infimum, of course, only over the lambdas for which this makes sense, gives us something meaningful. Good. Okay, but so this means I can now plug this in this estimate here, and at least I have something concrete, but still maybe it's not so clear what it really explicitly is. So what we have is the probability that our f of y, no, actually now it's this x here. So for this specific situation here, bigger than alpha, this is less than the infimum over lambda. And now I should restrict lambda between 0 and 1/2, because otherwise this guy here is infinity. And I still have here e to the minus lambda alpha. And here, in general, I have the expectation of e to the lambda g t. Yeah, and now, of course, this here was the sum. So I get here p factors of this form. So what I have here is actually this to the power p. Because this here is just one of the terms there. For the f1 is equal to g, for the f2 is equal to g, and for the fp is equal to g. And that's what we calculated. So namely, so this guy here was e to the minus lambda, but I take it to the power p, so I get e to the minus lambda p, and I have to divide it by the square root. So I have 1 minus 2 lambda. Square root is to power 1/2, but I also have the power p, so I have the power p over 2 here. Okay, and now, still, maybe this guy here is something which we don't really see directly how it behaves. Huh? And yeah, we really should see that the whole thing here behaves like e to the lambda squared. I mean, still the same as I said before. We have calculated explicitly, but from this explicit formula, we don't really see really explicitly how it behaves. Because I mean, the square root here, 1 over this will explode somehow exponentially, but it's maybe not directly clear from this. So I really should estimate this against concrete form. So that's maybe, let me formulate this in the next lemma, that really it's much better to give an estimate for this against something which we really want and can use later. So let me formulate this as a lemma. So we consider our variable which has a normal Gaussian distribution. So this is a one-dimensional standard Gaussian variable. And then I'm claiming that actually we really can estimate e to the lambda t squared minus 1 against e to the lambda squared times some constant, and here I can choose the constant e to the 2 lambda squared. And this is at least true for all lambda, not in the whole interval where this makes sense, but in the interval where lambda is less than 1 over 4. I mean, if here lambda goes to 1/2, of course this here will explode. This goes to infinity. So I should stay away from this. Okay, so I'm claiming this. And then this here will be something which I can manage later if I combine it with this one here. If I have it directly in this form, it's not so clear what to do. Okay, and the proof of this, yeah, of course, I mean, you can do it directly. We know what this explicitly is, so we should estimate this against this, which can be done. But actually, I also want to give another way, namely just by doing estimates for the moments, which might be more direct. In particular, I mean, yeah, it might not be clear why we should get here something like e to the lambda squared. Even if you look on this, might not be so clear. You can prove it somehow, but somehow it's not. If you don't know what you want to prove, it might not be so clear. So maybe I also do estimates for the moments where maybe it's getting a bit clearer, or the estimates show you more or less what you get. Clear up to now? Okay, I'm proving now this lemma, but of course the point is that it's true and we can use it later, but let me just prove it so that we see it explicitly. And yeah, the proof you can do either use the explicit form, which I'm not going to do. Yeah, do direct estimate. Yeah, just by showing that e to the minus lambda divided by 1 minus 2 lambda, the square root, is less than e to the 2 lambda squared if lambda is less than 1 over 4. Essentially, this is a calculus problem. And in all manuscripts which I looked up, it is said you can prove this by calculus. Just doing a curve discussion. Okay, when I tried it, I can almost prove it, maybe in a bit smaller interval. So it's a calculus problem, but it's not a straightforward one. Okay, but I mean, if you plot this curve, you see that it is true. And I mean, you can, by calculus, you can do it, but somehow it's not just one line. In principle, you would say, okay, I should see that something is monotone increasing, difference is bigger than 0, but the interval we are looking at is you go to the maximum and then you go down a bit again. So, okay, one has to discuss a bit more carefully, and somehow I don't find it very illuminating, and I don't really see, I mean, why should this be true? If you plot it, you see that it's true. Maybe you should do this, but maybe a nicer way, or Another way, which maybe tells you more why you have something like this, is if you're looking on the moments. I mean, this function here is a generating function in the moment, so if you have estimates for the moments, they should correspond to estimates for the moment generating function. And so maybe we should look on estimates for the moments of this t squared minus 1. So maybe that's what I don't want to do a bit more detailed. So, or estimate the moments of t squared minus 1. So the generating function contains the moments of this guy. So if you have estimates for this, it's okay. So we should have estimates for the moment of t squared minus 1 to the power k, for all k. And in principle, I mean, t is a Gauss, so I mean, we know the moments of a Gauss distribution. And so without the 1, it would just be the 2kth moment of a Gauss, for which we have an explicit formula. This minus 1 makes a shift, which makes it a bit more complicated, but still, in principle, of course, we reduce it to what we know about the Gauss. So let me write it like this. So it's less than the exponential, the expectation of t squared minus 1. And let me take now here the absolute value to the power k. I mean, this number is less than its absolute value, and I can bring in the absolute value in the integral. And so what I have here is now the integral over t squared minus 1 to the power k, integrated with respect to the density of the Gauss distribution. So that's what I have to see. And now what I want to do, I mean, the 2kth moment of t I know, so I mean, I want to estimate this somehow against the 2kth moment, and one can see that I can estimate it like this. If I integrate over this, that's what I know. That's what you had to do in, I think, the first assignment or so, calculating the moments of a Gauss distribution. And here I can estimate it like this, and this you can essentially, I mean, checking by looking on two cases. I mean, either the t is less than 1, which means this guy here, maybe let me write it down. So if the absolute value of t is less than 1, you are running here over all t. So you need this estimate to be true for all t. And here I have the absolute value, and so what I have here in between can be smaller than 1, but it can also be bigger than 1. And in both cases I have to do different things. So if the norm of t is less than 1, then what I have here is so t squared minus 1 to the power k is then, so if t is less than 1, then this guy is also less than 1, then the absolute value is actually 1 minus t squared to the power k, but this guy is less than 1, so this means this will be in any case less than 1. Okay, so if t is small, then this guy is less than 1, and that's the reason why I have a 1 here. Okay, in the other case, where t is bigger than 1, then t squared minus 1 to the power k. So if t is bigger than 1, then this absolute value is actually t squared minus 1, because this is bigger than 1. So this is t squared minus 1 to the power k. But now the t squared is bigger than 1, so I can just forget the 1. So this is less than t to the 2k. So you see, I mean, this thing here is either less than 1 or it's less than t to the 2k. So in any case, it's less than the sum of those two guys. Okay, that's a kind of trivial estimate I'm doing here. Okay, and so this is less than this. So this means the expectation of this is less than the expectation of this. And this is just the 2kth moment of my Gauss variable. And here I have 1. But the expectation of 1 is, of course, 1. And so you see, essentially, I have estimated against the 2kth moment of a Gauss. And this, we know what this is. And now I'm just massaging this estimate here a bit in a form which is somehow nicer. where somehow this 1 can also be brought in a form corresponding to this. So I mean, so what I have here, so what is the 2kth moment of a Gauss? This is this double factorial. So I mean, this is just 2k minus 1 times 2k minus 3 and so on. So I think this is something which we looked at in the first assignment, where you derived a recursion for how you calculate the moments. And then if you multiply this out, this is this, what is denoted with this symbol, double factorial of 2k minus 1, which means you take the product in a factorial way, but you're going down in steps of 2. I mean, double factorial is not the factorial of a factorial, but it means you do it like a factorial, but you are not going down in the factors in steps of 1, but you're going down in steps of 2. And here I have the 1. Okay, and I want to write this, maybe estimate this against something which, I mean, double factorial is something which I don't really know how to deal with this directly in terms of generating power series. In my exponential function, of course, I have factorials. So I want to write this and estimate this against a factorial, because then I really can deal with it easily. And so, I mean, so what is this? Yeah, let me write it down. So this is just 2k minus 1 times 2k minus 3 times 2k minus 5 and so on. And I'm going down up to 5 times 3 times 1. And then I have this additional 1. And now essentially I can estimate this. I have here the odd numbers, but I can estimate this, each of them, against the closest, the next highest even number. And then actually each even number has a factor of 2, which I can take out, and then I'm really left with the ordinary factorial. So I mean, I estimate this here against the 2k minus 1 is less than 2k. The 2k minus 3 is less than 2k minus 2, and so on. The 5 is less than 6. The 3 is less than 4. And the 1, okay, I'm leaving. And actually, in order to deal with this, I say, okay, replacing the 3 by a 4 was not so good idea. Maybe I take this back. But I have the 4 here because let me see, I should. Yeah, okay, because now I can divide out the 2's out of this, and then I have here the factorial. So this is less than, I mean, I have a factor 2 in each of those guys, and how many of them do I have? I have 2 to the k minus 1. Yeah, okay. So I'm not writing a 2 here. So I don't have the last one. I'm not changing the 1 here to a 2, and I'm actually also not changing the 3 to a 4, because I write this. But for doing this reduction, I'm writing it down here. So I divide out the 2, so I have k minus 1 2's, and then I'm left with k factorial, because here I have here k minus 1, and so on, times 3 times 2. Okay, and then a 1 I can put anyhow as I like. So I have this, but I also have this 3 over 4, and then I have this 1. And why do I want this strange 3 over 4 here? Because I can estimate the 1 against 1 over 4 of this, so that I just get somehow rid of the 1. So I say that this 1 here is smaller than the same thing here, 2k minus 1, k factorial, times 1 over 4. And this is true for all k bigger than 2. I mean, 1, of course, is usually very small compared to this. Only for the small k, it's the same order. For k equal to 0 and k equal to 1, this is not good, but this here is for k greater or equal to 2. I mean, because for 2, I have here 2 to the 1 times 2 factorial. So this is 2 times 2 divided by 4, this is 1. And for the bigger case, it's also true. So I can estimate this against this, and then the 3 over 4 and the 1 over 4 gives me a factor 1. So what I really have now is that I have estimated this against 2k minus 1 times k factorial, and this is true in this setting here for k bigger than 1. Okay, maybe a lot of strange estimates, but what I have in the end is I really have a nice estimate essentially against the factorial. That's what I want, because this is something I can easily now use for estimating my generating power series. Yeah, now I want my power series. So what I really want to estimate is the expectation of e to the lambda t squared minus 1. But of course we know that this is the generating power series of the moments. So this is the expectation of the sum k from 0 to infinity, lambda to the k, t squared minus 1 to the k divided by k factorial. Okay, and then what I have calculated here was essentially an estimate where I had the absolute value here. So I can estimate this against where I'm also putting the absolute value here. And then I have here the sum kc 0 to infinity, lambda to the k, k factorial comes out, and I'm left here with the expectation. So the expectation applies to this of the absolute value, or the absolute value maybe here, of t squared minus 1 to the k. And that's, so this is the moment, the kth moment of t squared minus 1, but this is exactly what we estimated here. I mean, that was the whole thing which I did here, to estimate this against 2k minus 1 times k factorial. And you see why I want to write it like this, because this goes away with this. But actually, I'm summing here from starting from 0, but this is only true for k bigger than 2, so I have to be careful about the first and the second term. So this here is for k greater or equal to 2. So this means I should take the k equal to 0 term separately, but this is just 1. Then I should take the term k equal to 1. But for k equal to 1, I take the expectation of t squared minus 1. And t squared minus 1, yeah, what is the expectation of t squared minus 1? What is the first moment of t squared minus 1? Or what is the expectation of t squared? For my Gauss, for my standard Gauss, yeah, 1. Yeah. So the expectation of t squared is 1, so t squared minus 1 has expectation 0. I mean, that's essentially also the reason why my function, I choose my function as t squared minus 1, because this is something which has expectation 0. And the expectation is not really showing up in my inequality which I have, but I want to compare things with its expectation. Anyhow, so this means that the term here k equal to 1 is actually equal to 0, so that's good. I don't have to put it down, and then I'm just left with k starting at 2, and then of course I have this estimate here, k factorial cancels this one. Here I have 2 to the k minus 1, here I have lambda to the k, so maybe let me also write this as 2 to the k and correct with an additional 1/2, which I can then take out, because this I'm doing for all k. So I have a 1/2, and then I have here my sum starting from 2 to infinity, and what do I have here? So this is gone away, and then I have lambda to the k and 2 to the k, so I have 2 lambda to the power k. Right, actually nothing left anymore. Okay, and so this is essentially now a geometric series. And now you also see why lambda should not be bigger than 1/2. I mean, that's where this guy breaks down. I mean, we see it in the explicit formula, but also here in the estimates, you see that essentially we seem to be in the right order. I mean, the geometric series only converges if this guy here is less than 1, which means lambda should be less than 1/2. Okay, so this is the geometric series, which starts not at 0, but at 1. So this means we should take here out a 2 lambda to the squared, and then I'm left with the geometric series in 2 lambda. So it's 1 divided by 1 minus 2 lambda. Yeah, or maybe let me write it again. So it's 1 plus, I have this 2 lambda squared divided by 2. This is this 2, and here I have 1 minus 2 lambda. 1 minus 2 lambda. Okay, and now I just estimate this against 1 plus 2 lambda squared if in the right domain for lambda. Of course, if lambda, I mean I'm estimating just what I have here against the factor, let's say 2. So this 1, no, I have 2 terms. I divide this. Okay, so okay, I have, so this is correct. I have this 1/2 is here, 2 lambda squared. I take out of this sum here, and then essentially I have the geometric series starting at k equal to 0, which is 1 over 1 minus 2 lambda. Yeah, okay, but now I estimate this against, okay, I have the 1. And now I wanted to say that this guy here, I estimate this against, okay, I have the 2 lambda squared in the numerator. And I just, okay, I want to estimate this division here. Of course, if lambda goes to 1/2, this here explodes. But if let's say lambda is less than 1 over 4, then the biggest I'm dividing here is 1 minus 2 times 1 over 4. So it's I'm dividing by 1/2. Yeah, I'm dividing by 1/2, which means here with this factor 2, I'm just dividing by 1. Okay, so it seems to be it's less than plus 1 over 4 lambda squared. Is this correct? Do you agree? Or I mean, I have here 2 lambda squared instead of 4 lambda squared. But now I don't see why I should have a 2 there. I mean, this guy here in the bottom, this is for lambda less than 1 over 4. This is bigger than 1. Huh? Okay. Okay, so maybe it's a 4. Maybe, let's see, maybe that's shouldn't make a big difference, but okay. Yeah, okay, and then of course, I mean, I want to have an exponential estimate. And now I'm just estimating this against the exponential function. So now I'm estimating this against e to what I have here, and now it should be, okay, according to this, it should be 4 lambda squared. I mean, this is if e to the x, I mean, this is the beginning of the Taylor series of e to the x. So this is 1 plus x, and this is e to the x. And of course, I'm on the positive side. Yeah, 1 plus x is less than e to the x. Okay, but now I have here 4 lambda squared. And in my lemma, I promised you a 2 to the lambda squared. But okay, now, at the moment, it seems to be a 4. Okay, but 2 or 4, maybe that's the reason that the 8, which I changed at the beginning, is indeed a 16. I don't know. Let's see. Okay, so let us continue with the 4. And see. And I mean, those are constants which should not make a big difference. So the main thing is the lambda squared is showing up. Good, but now we have the main estimates together. So I mean, we really have now estimate for this, and now we can try to get the best value for lambda. Okay, but so now let's see how we can really do them. I mean, now comes the main step. Oh, I mean, now we have things so explicitly that really it's very easy to find the infimum over this and get a concrete estimate. So this is now we really do the proof of our main theorem for the concentration of the norm of our variable. So that was our theorem 2.2. So what we have to estimate, I mean, we reduced the estimate for the norm to an estimate for the norm squared. So what we really have to estimate is the probability that the norm of x squared minus p is bigger than, and then going over from the norm to the norm squared gave us the square root of p here. Yeah, and now, of course, so what I have here, this x squared minus p, let me write it again. So this is our function f, x squared minus p, which I have written as a sum of those functions g1 up to gp, where those guys here are independent, and each of the coordinates has, and each of this function here is t squared minus 1, and the t's have a standard normal distribution. So just repeating the specific setting which we have here. So t is a normal standard distribution. And then, so what we get, this probability that this absolute value is bigger than this, means either the absolute value is positive and then it's bigger to this, or the absolute, okay, so this means what I have inside the absolute value is bigger than this guy, or what I have inside is actually negative and it is smaller than the negative of this. So for the absolute value bigger than something, essentially this means I have two estimates in one direction and in the other. So this means the fact that the norm of f is bigger than this is the same as that either f of y is bigger than this guy without the norm, or that f of y is smaller than the negative of this guy. And those are events which are exclusive. So f of y can only be bigger than the plus side, or it can be smaller than this. So the probabilities of this just add up. So plus the probability that f of y is less than minus epsilon square root of p. Just saying that the square root of that the absolute value of this is bigger than this is the same as saying either I have this is bigger than this or this is smaller than this. Okay, and those two events are disjoint, so I have here the sum of the probabilities, and actually it's symmetric, so the probability of this is the same as the probability of this. This means I get a factor 2, and you remember in my theorem I had an overall factor 2 at the beginning. This is coming from this. So what I have here is just 2 times, let's say, the probability of this, that f of y is bigger than epsilon times the square root of p. And now we are really in the setting which we had before. But before we had no absolute value. And now, I mean, yeah, now the alpha is this epsilon times the square root of p. So alpha, let me call this alpha. And then I'm using, essentially what I have here. So this is less than, I have this factor 2. And then I have the infimum of the lambda between, in principle, could be between 0 and 1/2 e to the minus lambda alpha, and then I have the expectation. Let me write it again. Expectation of e to the lambda t squared minus 1. So that's the expectation of e to the lambda g of t. G of t is t squared minus 1. And then I have p times the same guy, so I have this to the power p. Yeah, and now we have just estimated this guy here. Okay, we have estimated it now by e to the 4 lambda squared. For lambda is less than 1/4. And so this means, okay, the lambda bigger between 1/2 and 1/4 I cannot use. They are don't give anything meaningful. So I have to look here in the domain between 0 and 1 over 4. So it's 2 times the infimum for lambda between 0 and 1 over 4. And then I have here now an exponential. Here I have minus lambda alpha. And here I have plus 4 lambda squared. Okay, and of course I have here to the power p. That's of course the important point. I mean, I have dependency on the dimension here. So this here is multiplied with p. Yeah, and now of course the idea is just I want to find the minimum value here in the exponent. So I want to choose the lambda. I mean, I'm free to choose the lambda in this domain such that this here gives me the best estimate. And of course I want here a minus sign. Of course, I mean, I want e to the minus. It should be an exponential decay of the probability t. So of course the idea is that, I mean, if I have my lambda here, I mean, I have somewhere 1 over 4. And of course for lambda equal to 0, I mean, this is just 0, so it's e to the minus 1. So it just says the probability is less than 2 times 1, which is of course useless. So this means, of course, I mean, I could choose any specific lambda here, but of course the only concrete one is lambda equal to 0. But there I have an estimate which is not useful. So the idea is that this here goes down. Yeah, this exponential thing goes down somehow and then maybe grows again, and I want to find the value lambda 0, where actually this here gives me the smallest value. Okay, so for this I just take the derivative and see whether the derivative is equal to 0. So what I want is to find the minimum of what I have here in the exponent of my exponential function. So it's minus lambda alpha plus 4 lambda squared p. Okay, and so I take the derivative and yeah, should check that it really is a minimum. This should be okay. Taking the derivative with respect to lambda, so this gives me minus alpha, and here I get 8 times lambda p plus 8 times, and let me call the minimum lambda 0, lambda p, and the condition is that this derivative is equal to 0, which means the lambda 0 is alpha divided by 8 times p. Yeah, okay, and then of course the alpha, now let me write it in terms of the epsilon, what I really want in my starting inequality. So the alpha is epsilon times the square root of p. So this is epsilon times the square root of p divided by 8p. So this is epsilon divided by 8 times the square root of p. And maybe we should make sure that we are really here in a domain between 0 and 1 over 4, because if the lambda 0 would be somewhere here, then of course those estimates are not true. And I mean, this is less than, actually in this case it seems to be less than 1 over 8, because we have chosen the epsilon, we have restricted them to a specific domain. So I mean, this here is true because we consider in our theorem only epsilons which are small compared to p, and actually should be small compared to the square root of p. So our condition was that epsilon is between 0 and the square root of p. So epsilon divided by this is less than 1. So actually this is smaller than this. So this is okay. This really is in a domain where everything fits if we take epsilon of this size. So epsilon should not be of the order p or something like this. Good, okay, but then this is the lambda 0, and then we can plug this in our estimate here. So now we choose, so this is, yeah, we choose now for lambda, we choose lambda 0, and then of course we get here specific exponent. So So what? So we have minus lambda 0 alpha plus 2 lambda 0. No, actually it's 4. Okay. Minus this plus 4 times. That's what we want. And now lambda 0 is what is it? Yeah, this guy here. Or maybe let's do it first in alpha, and then at the end plug in the epsilon. Okay, so it's minus lambda 0 is alpha divided by 8p times alpha, so I get an alpha squared, plus 4 times lambda squared, so this is alpha squared. Okay, but now I get 8 squared here. I'm not sure whether this is better than what I had before, but so it's 64 p squared times p. Okay, and so you see, I mean, they fit now together, the two guys. Huh? I have alpha squared, 1 p goes away, so they are both divided by p. And so let me see, this here is 1 over, okay, so I have a minus sign. This is the bigger term. I have alpha squared divided by p, and here I have minus 1 over 8, and here I have plus 1 over 16. So what I have is 1 over 16, no? Which was my original. I shouldn't have changed my my lemma, huh? So, or my original statement. Huh? So I'm really back to minus 1 over 16. Oh, okay, so maybe this was the better calculation. Okay, and now of course, okay, now I plug in for alpha. That was epsilon times square root of p. So this means I have minus 1 over 16. Alpha squared is then epsilon squared times the square of the square root. So it's p and divided by p, and now the p goes away. Huh? So it's really minus epsilon squared over 16. And that's what I was claiming in this this theorem. So maybe what have we seen here? So the probability of the Gaussian vectors in R to the n such that the norm has a distance to the square root of p which is bigger than epsilon. This we have seen in the very first step, that this is the probability of the random vectors in R to the n for which the square of the norm has a distance to p bigger than epsilon times the square root of p. And that's what we just estimated here, that this is less than, so we had this factor 2, and then we estimated this here. This is now less than e to this thing here, e to the minus epsilon squared divided by 8. Okay, and that's the end of the proof. So I hope it's okay. I mean, I also tried to develop the general machinery. So of course you can apply such things also to other situations, but here we can do things very explicitly. And yeah, you see we get an exponential concentration quantity. That's what usually you expect and what you can prove with such tools. Good, but maybe yeah. Final remark, which I'm not going to write down, but just say it. So I mean, what we have seen here is the general machinery, and what we have used is that our function is essentially a sum of independent guys. Okay, and then yeah, we come to this setting, and then what we need essentially about the distribution of this g of t is that we can estimate its moments essentially against the factorial, or we can estimate its moment generating function essentially against e to the lambda squared. Because I mean, if you have this, then this here works in the same way. Maybe the constants are different, but you get the same thing. So that, I mean, if you have a sum of independent variables, and the variables have a distribution for which you have that moment generating function behaves like e to the lambda squared, then this works in the same way. Then you have a concentration. Okay, and there are many distributions which have this property, and they are usually called sub-exponential distributions, because they can be compared with this exponential. So sub-exponential distributions are a big class of important distributions for which you can prove essentially in the same way this concentration phenomena. Okay, and so what we showed here is that the square of a Gauss, so our variable which we considered was not the Gauss, but it was the square, t squared minus 1. And we showed that this is sub-exponential, and then this works. Okay, and so, I mean, the theorems which we get here, so this is essentially what is called Bernstein inequality. That's this concentration inequality for, let's say, in general, sub-exponential distributions. And there are variants of this, where maybe the assumptions are a little bit different, but still the whole machinery works. And I mean, there are other inequalities which go either under the name of Chernoff inequality or Höfting inequality, but they are all variants of the same idea. So it's really about using Markov for the moment generating function. And then you get those kind of concentration inequalities for linear functions, for linear function, for sums of independent guys. Of course, that's something that's very important. But maybe what is more important for us, more interesting, is if we look on functions which are not linear. Because, I mean, in particular, neural networks are somehow functions of the input data, but of course they are not linear. And so we should hope for that maybe also we can understand or get concentration in more general situations. And that's what is really the case, and that's what I want to do next time, or talk about this. And this is more Talleyrand kind of inequalities, which, of course, you must have special assumptions on your functions. So you cannot expect concentration for everything, but you have a big class of nonlinear functions for which you also have concentration. Good. Okay, that's it for today.